Hello, welcome to my presentation about smart manufacturing and additive manufacturing. I am Christian J. A. Uwayan, a registered mechanical engineer. Today we will discuss about first, the smart manufacturing overview. Next is the design for the smart manufacturing systems. Third, the digital technologies available for smart materials and processes. And aside from smart manufacturing, we will also tackle about the additive manufacturing, its overview. Next, we will also delve deeper in the additive manufacturing process. And lastly, we will explore the available additive manufacturing technologies. Smart manufacturing overview. Smart manufacturing, or commonly referred to as Industry 4.0 in Europe and Made in China 2025 in China. This is a fully integrated and collaborative manufacturing system that responds in real time to meet the changing conditions in the factory, supply chain, and customer needs. Also, it uses information technologies, computer integrated technology or CAT, flexible workforces, and lastly the digital technology to improve the system adaptability for the changes and uncertainties in system operations. What does being smart covers? Being smart means that you should have the ability to communicate, to exchange data, and to collect and report data regarding the state of manufacturing assets. So a smart system, you should have it's based on data. So you need to collect more data to be able to gain understanding on and also formulate patterns in order to determine what is the problem or formulate a solution. Also, being smart contains the embedded knowledge for the representation of human expertise and the understanding of system elements and environments. Learning capabilities through the application of diversified algorithms, methods, and tools. Fourth is the reasoning capabilities for data-driven decision making. Fifth is the perception capability to sense, understand, and respond to environmental changes. So the perception capability refers to the ability of the smart system to respond or to formulate actions or corrective actions. Also, it has the control capabilities to ensure smooth manufacturing processes and to make and deliver products to the end users. Also, being smart means you have to self-organize to reconfigure systems to accommodate changes and uncertainties. And lastly, context awareness that retrieves the information and knowledge that characterizes the state of systems and environments. So what context awareness means is that the system can able to identify what's wrong with the system. So he can alert or make informative decisions or suggest actions that could minimize the downtime or the breakdown of the equipment. The main characteristics of a smart system is that we have 5. First is the connectivity. So connected to all smart things through internet, enabling collaboration and collaborations across departments. So this usually involves the Internet of Things, in which the smartphones can gain access to the data over far areas that we need to be informed about. Also, the optimization for predictable capacities, increased asset uptime and efficiency, highly automated production and material handling, and minimize cost. So optimization is very important as we apply our knowledge in operations research. So we need to understand how to allocate our resources so that we can use them wisely and reduce the costs and also increase the for instance the sales. Also transparency, third characteristic. Transparent for live metrics and tools and have real-time linkages to demand forecasts and order tracking. So this is very important in a smart system since all workers have to be informed in such data so that they can be aware on what they are lacking, or so that they can correct also, and also they can be more productive since they have the target and they have the capability to increase the production output. The fourth characteristic is the proactive. Proactive for anomaly identification and resolutions, restocking and replenishment, and identification of quality issues. So the fourth one is very important characteristic of a smart system since the smart system should have a advanced decision making. So it should have a suggestion on what the trend is, what the trend means, and also like the predictive maintenance. So when a particular equipment or part such as bearing starts showing defects or showing defective plot of the vibration or temperature, the predictive maintenance team can resolve the issue, and also you can estimate the time that the bearing would last. Fifth characteristic is the agility. So agility for flexible and adaptable scheduling and production changes with configurable machines and layouts. So smart system need to be agile so that it can be easily replaced or configured so to meet the changing conditions and demands. Design of smart manufacturing systems. 3 iterative phases. Since a smart manufacturing system aims for system adaptability in dealing with changes and uncertainties, and such a capability is achieved by either the flexibility of the system elements or the configurability at a system level. Design of a manufacturing system involves 3 iterative systems in its system life cycle. First is the system design. A set of functional requirements, FRs, is defined. Available physical assets and accessible virtual assets are considered to define a design space with all feasible design solutions, and the system for performances are ranked to define a set of prioritized performance metrics. So in the system design phase, we need to identify what is the function of an equipment, and also we need to list down the available assets, whether it can be virtual or physical. Also we need to define a metric on how to measure the functionality of these requirements, or on how these requirements are met. Second phase is the system operation. Design analysis and synthesis are performed to optimize a system and thus implement it in application. All smart things in the system are monitored to determine if the system element or whole system has to be reconfigured to meet the identified changes. So in this phase, the design is implemented. Third is the system reconfiguration. Either system elements or the whole system is reconfigured to make the smart manufacturing system sustainable. So based on the changes or on the system elements, factors that changing the system elements, whether they are also relevant or it has changed over time. So we need to reconfigure our system so that it can attend to the needs of the production. So here we can see that the top portion is the system defined phase, where we need to identify the FRs or functional requirements, the possible solutions, and the performance metrics. The middle one is the system operation phase, where we perform design analysis and synthesis. Also, we need to implement our digital technologies such as digital twin and SOS, so that we can have idea on how the system elements interact with the system, which can be measured by the parameters. Also, the system states. We need to identify what are the system parameters, such as the let's say the KPI, the overall performance of the production also, whereas the individual or system element parameters are the temperature, the pressure, which can be observed in a machine or a part. The third phase is the system reconfiguration phase, where we need to assess whether the system is to be changed in order to meet our performance metrics. And likewise, the system elements is also reconfigured, whether we can make it more efficient, and also whether it can resolve the problem. Digital technologies for smart materials and processes. Traditional versus digital technology. Similar to traditional manufacturing, smart manufacturing aims to make and deliver products to users. However, products from smart manufacturing are generally more advanced in terms of their intelligence level, functionalities, and more importantly, their sustainability from the perspectives of economy, environment, and human society. First, digital technologies available is the digital twin, or DT1, which can be seen as an example in the right image. We have the pump or motor with the base plate. It is replicated through 3D modeling. It can be seen at an iPad or a computer, and it can be monitored without going to the site. So modeling and simulation tools used to be standalone system that were widely applied to predict system behaviors based on assumed conditions, changes, disturbances, and randomness. Digital twins has enabled the interactions and integrations of information and physical worlds in real-time manners. So I have experienced the digital twin since my previous plant modeled our power plant, and it is done so that the parameters such as pressure and temperature can be monitored, and also vibration can be monitored in real time, so that the field engineers can go and can, or the control room operators can can ask for the field engineers so that they can go to the site and verify whether this equipment is still has the high vibration or high temperature according to the virtual model. Second technology for applying the digital technology is the cyber physical systems or CPS. CPS supports real-time communication and interaction of cyber and physical systems to close control loops, monitor system states in real time, and adjust system behaviors promptly when the changes are detected. CPS makes manufacturing systems smart by improving the responsiveness, adaptability, and predictivity of system elements and facilitating the collaboration of stakeholders in the entire process of mass customization of products. So example of a cyber physical system is the in my previous experience also I have encountered the continuous emission monitoring system where the inputs are the materials used for combustions, and we can predict or we can have an idea on the output, and also we can monitor its amount, whether it can be detrimental to the environment, so that we can control our input, and that is the corrective action. So less emission or that contributes to the global warming means cost reduction, since we are not liable for fines. Third technology using the digitization is the cloud computing. Modern manufacturing systems tend to be decentralized and distributed, while decision-making activities for smart manufacturing are facing a number of challenges, such as sharing and accessing data in distributed environments, storing and maintaining an ever-increasing amount of data in the network. 3. The high demand of computing to optimize decisions with a limited local computing resources. 4. Is the complexity of coordination among manufacturing resources. So the cloud computing is very well known today, but however some developing countries still not use the cloud computing capability of, for example, Google, which some companies utilize for their spreadsheet making and collaboration through paperless, and also they can access the data as long as it is not protected or hidden. Also, it can also optimize the decision, since all parties can see the progress of a report. Also, you can easily compute, since they have a very large servers, or has large capacity of servers which can compute at a faster rate. Now, we are done with the smart manufacturing. We now proceed to the additive manufacturing technology. Additive manufacturing, or 3D printing, has unparalleled customization capabilities, reduced waste, and the ability to fabricate complex geometries that are difficult or impossible to achieve with traditional manufacturing methods. Since its inception in 1980s, 3D printing transitioned from a rapid prototyping tool to a viable manufacturing method for a broad spectrum of applications, including aerospace, automotive, healthcare, and fashion. So what is its difference between the traditional methods, such as the formative and subtractive manufacturing? 3D printing is ideal for prototypes and small production runs. However, in formative and subtractive, they are ideal for mass production due to low cost per part, or they utilize the economies of scale. 3D printing also is limited by material variety, part size, and requires significant post-processing, potentially leading to anisotropic mechanical properties. So In the 3D printing, as we prepare the STL file or the G code, so we can observe that the 3D printing has infills or the pattern of the print. In some areas they are not uniform, such that they can be easily that it can easily break due to shearing force, and that is the disadvantage of 3D printing. However, in formative and subtractive manufacturing, they offer superior mechanical strength, isotropy, and surface finish due to wider range of materials and established processes. Challenges in future development. Despite the remarkable achievements of 3D printing technology, encompassing a wide range of industries with its innovative applications, it continues to face the following significant limitations. First is the speed of printing, which, despite improvements, remains slow for mass production applications. Second is the range of materials suitable for 3D printing. It still lacks the diversity and performance characteristics of those used in traditional manufacturing processes, since most common 3D printing material is the PLA or polylactic acid, and also the ABS. So they are very inferior compared to the molding technology, where they can use the polyethylene and also polycarbonate. Third challenge is the resolution and surface finish of printed objects often require extensive post-processing to meet industry standards. So the resolution and surface finish, because the 3D printing operates by layering, so that it is also inferior with the subtractive and forming technology. So since its surface is not that yet polished or not that yet perfect. Fourth challenge is the cost of 3D printers and materials can be prohibitively high for widespread adoption. So 3D printers cost around, or high-end 3D printers like the Prusa i3 Mark II cost around 40 to 45,000 pesos if purchased. So how does additive manufacturing work? First step of the additive manufacturing process is the design and modeling. So it utilizes computer-aided design software where engineers can craft detailed and complex digital representations of the desired object. Second is the conversion to STL or stereolithography file. Once the 3D model is complete, it is exported as an STL file. This format simplifies the model by breaking down its surface into a series of triangles, also known as tessellation. So this STL is usually done using for example, conversion to STL. It is done through CAD, where you can export your file into .stl file for later slicing. The third step is the slicing, where in a specialized software, or commonly in the a slicing software, for example, the slicer, where the Prusa 3D printer uses, or the Ultimaker Cura, where the Ultimaker 3D printers use. So slicing transforms the STL file into a series of thin horizontal layers, and the primary output of this process is the generation of G code. So this G code is now the program that will be required by the machine or 3D printer in order for the extruder to move at different axes at a programmed manner. The last step is the preparation, printing, and post-processing. In the preparation phase, the material preparation, the bed leveling, preheating of the extruder body, and printing, where the printer nozzle or laser follows the path dictated by the G-code. And lastly, post-processing, where the support removal, surface finishing, and painting is performed. The image here is the four steps or phases of the process, where I will give emphasis to this fourth one, the 3D printing and post-processing, since from the previous slide, we need first to prepare the material. So we need to load the filament in the 3D printer. Next is the bed leveling, where some points in the heat bed is calibrated so that the ejection of the filament is level and the first layer is successful. And also we need to preheat the extruder body so that when the filament comes into the extruder, it can be easily melted. In the printing phase, where the printer's nozzle follows the path dictated by the G-code, so the printer now moves from X to Y direction, and once it finishes the layers in that X and Y dimension, it now proceeds at a Z, but however it will take some time to proceed to an upper level. The post-processing part is that the support are removed. So since some 3D printed parts require support so that it will not fall, the maximum or the suggested support angle is based on my experience is 45 degrees, or the most it can also print 30 degrees with respect to the build plate. Lastly, the post-processing, such as the support removal, surface finishing, where the output is submerged in a chemical, or so that its surface will be improved. The chemical, for example, the acetone, for the ABS to have shiny or glossy appearance. You can also paint the products and sell them as a figurine or other purposes. Lastly, the additive manufacturing technologies. Most common additive manufacturing technologies. First is the material extrusion, or FDM. Fused deposition modeling printers involves the creation of parts by extruding thermoplastics layer by layer. The main advantages of FDM printing are the low price, their ability to be reproduced, their speed efficiency, and low maintenance. However, this type of printer typically require a high temperature and supports for angles greater than 45 degrees. These supports lead to materials being wasted and increased production time. So, as we can see here, this is the most common type of 3D printer, where the material is expelled through the nozzle and successively and it is ejected to the build plate until it is stable and the model is formed. Second, additive manufacturing technology. The VAT polymerization, or the SLA, which is common. The SLA is the most common VAT polymerization technique. The VAT polymerization uses light source to cure a photopolymer resin contained within a reservoir. SLA utilizes a laser to cure a photopolymer resin onto a build plate in the desired geometry. One of its primary benefits is the ability to produce parts with exceptional detail and surface finish, but its drawback include limited build volume, brittle resins, not possessing strength, and also the shrinkage. So as we can see in the right image, we have a laser which points to a mirror, and this mirror uh, relays the laser beam into the resin, and once the laser contacts with the resin, it cures the resin and forms a solid. And once the first layer or a layer is finished, the build plate is um, uh, the build plate is moved upwards, but in a gradual manner. The third additive manufacturing technology is the binder jetting. Binder jetting was developed in MIT in the 1990s. The printing process of binder jetting consists of a binder being printed into a bed of powder to form the cross sections of a print, similar to powder bed fusion printing. This is recognized for its low or cost effectiveness, which stems from the efficient use of materials. Common materials are ceramics, metal, and polymer. It can also minimize the occurrence of heat-induced distortions. Its disadvantage is low density output, labor-intensive post-processing, and susceptible to deformation during removal of supports. So the image in the right side here is an example of binder jetting machine where a print head moves in the X and Y direction, and it ejects a liquid adhesive or a binder material. And the powder bed is being fed by this leveling roller, where this powder came from the powder feed piston delivered from the bottom of the machine, and this powder is, once the layer has been cured, it delivers a flat or a leveled powder for the next layer to be cured again. So that is the end of my presentation. Thank you for listening.